Hello, niece and nephew, welcome back to chapter 4 of computer networks. This is a part 2 of network layer. In part 1, we introduction into network layer, and in this video, we're gonna talk about network layer protocols. Okay, let's go. In this section, we show how the network layer is implemented in the TCP/IP protocol suite. The protocols in the network layer have gone through several versions. In this section, we concentrate on the current version. In the last section of this chapter, we briefly discuss version 6, which is on the horizon. Here is a figure of position of IP and other network layer protocols in TCP/IP protocol suite. Packets used by the IP are called datacams. Figure 4.24 shows the IPv4 datacam format. A datacam is a variable length packet consisting of two parts, header and payload. The header is 20 and 60 bytes in length and contain information essential to routing and delivery. It is customary in TCP/IP to show the header in 4-byte sections. The topic is fragmentation security of IPv4 datacam. Here is a figure of IP datacam. Okay, and this is multiplexing and demultiplexing using the value of the protocol field. Here is maximum transfer unit or MTU. This is a figure of fragmentation example. And this is detailed fragmentation example. The identifier used in the IP layer of the TCP/IP protocol suite to identify the connection of each device to the internet is called the internet address or IP address. An IPv4 address is a 32-bit address that uniquely and universally defines the connection of a host or a router to the internet. The IP address is the address of the connection, not the host or the router, because if the device is moved to another network, the IP address may be changed. Here are topics of IPv4 addresses. It contains address space, notation, hierarchy in addressing, classful addressing, address depletion, classless addressing, dynamic host configuration protocol or DHCP, and NAT. This is a figure of three different notation in IPv4 addressing. Wow. Hierarchy in addressing. Occupation of the address space in classful addressing. Variable length box in classes addressing. Slash notion. And information extraction in classes addressing. Example 4.1. A classless address is given as 167.199.170.82 with 27. We can find the above three pieces of information as follows. The number of addresses in the network is 2 raised to the power of 32 minus n equals 2 raised to the power of 5 equals 32 addresses in the first address can be found by keeping the first 27 bits and changing the list of the bits to zeros. The last address can be found by keeping the first 27 bits and changing the list of the bits to ones. Example 4.2. We repeat example 4.1 using the math. The math is in dotted decimal notation is 256.256.256.224. The AND, OR, and NOT operations can be applied to individual bytes using calculators and applied at the book website. Example 4.3. In classless addressing, an address cannot specify the block the address belongs to. For example, the addresses 230.8.24.56 can belong to many blocks. Some of them are shown below with the value of the prefix associated with that block. Here is a figure of network address. An ISP has requested a block of 1000 addresses. Since 1000 is not a power of 2, 1024 addresses are granted. The prefix range is calculated as n equals 32 minus log base 2 of 1024 equals 22. An available block 18.14.12.0/22 is scanned to the ISP. It can be seen that the first address in decimal is 302,910,464, which is divisible by 124. Example 4.5. An organization is granted a block of addresses with the beginning address 14.24.74.0/24. The organization needs to have 3 sub-blocks of addresses to use in its 3 subnets, 1 sub-block of 10 addresses, 1 sub-block of 60 addresses, and 1 sub-block of 120 addresses. Decide the sub-blocks. Here is a solution. They are 2 raised to the power of 32 minus 24 equals 256 addresses in this block. The first address is 14.24.74.0/24. The last address is 14.24.74.255/24. To satisfy the third requirement, we assign address to sub-blocks, starting with the largest and ending with the smallest one. Example 4.5 continued. A. The number of addresses in the largest sub-block, which requires 120 addresses, is not a power of 2. We allocate 128 addresses. The subnet mask for this subnet can be found as n1 equals 32 minus log base 2 of 128 equals 25. The first address in this box is 14.24.74.0/25. The last address is 14.24.74.127/25. B. The number of addresses in the second largest subbox, which requires 60 addresses, is not a power of 2 either. We allocate 64 addresses. The subnet mask for this subnet can be found as n2 equals 32 minus log base 2 of 64 equals 26. The first address in this box is 14.24.74.128/26. The last address is 14.24.74.191/26. Okay, let's go. C. The number of addresses in the smallest subbox, which requires 10 addresses, is not a power of 2 either. We allocate 16 addresses. The subnet mask for this subnet can be found as n3 equals 32 minus log base 2 of 64 equals 28. The first address in this box is 14.24.74.192/28. The last address is 14.24.74.192/28. If we add all addresses in the previous subbox, the result is 208 addresses, which means 48 addresses are left in reverse. The first address in this range is 14.24.74.208. The last address is 14.24.74.255. We don't know about the prefix range yet. Figure 4.36 shows the configuration of box. We have shown the first address in each box. Solution to example 4.5. A is the original box, B is subbox. Example 4.6. Figure 4.37 shows how 4 small boxes of addresses are assigned to 4 organizations by an ISP. The ISP combines these 4 boxes into one single box and advertises the larger box to the rest of the world. Any packet destined for this larger box should be sent to this ISP. It is the responsibility of the ISP to forward the packet to the appropriate organization. This is similar to routing we can find in a postal network. All packages coming from outside a county are sent first to the capital and then distributed to the corresponding destination. And here is an example of estate aggregation. Estate aggregation as the summarization of large summarization box of addresses are combined to create a larger box. Routing can be done based on the prefix of the larger box. This is the chapter 4, part 2 summary. The internet is made of many networks or links. connected through connecting devices, each of which acts as a router or as a switch. Two types of switching are traditionally used in networking: circuit switching and packet switching. The network layer is designed as a packet switch network. The network layer supervises the handling of packets by the underlying physical networks. The delivery of a packet can be direct or indirect. Two categories of forwarding are defined: forwarding based on the destination address of the IP datagam and forwarding based on the label attached to an IP datagam. IPv4 is an unreliable connectionless protocol responsible for source-to-destination delivery. Packets in the IP layer are called datagam. The identifiers used in the IP layer of the TCP/IP protocol suite are called the IP addresses. An IPv4 address is 32 bits long, divided into two parts. The prefix and the suffix or addresses in the block have the same prefix. Each address has a different suffix. Okay, this is the end of chapter 4 part 2. See you again next time. Bye bye.